Hey guys, welcome back. This is going to be part 2 of the 7.1 instructional video. Please stop the video if you have not watched part 1 yet. Go back and watch 7.1 part 1. What it will do is introduce what our topic for the chapter, which is systems of linear equations. Part 1 will introduce what a system of linear equations is. It will show you the beginning steps of how do we solve systems of linear equations and explain what a solution to a system of linear equations means. It will also then go through some examples where we find solutions to systems of linear equations. If you have not watched part 1 yet, please stop the video and go ahead and watch part 1. If you have watched part 1 and you were very confused by it, please, again, stop this video and email me. Let me know what's tripping you up so I can help you out. So we're going to continue off what we learned in part 1. In this case, we have another system of linear equations, and our goal is to solve it. To find a solution, find the ordered pair or pairs that will make the system of linear equations true. Or rather, we're going to find the ordered pair that will satisfy the system of linear equations. Okay? So what we're going to do here is we are going to graph. That's what we do in 7.1. We solve systems of linear equations by graphing. So what I'm going to do is I'm going to graph the first linear equation in blue. I have a it's in slope-intercept form. Hopefully you remember that from chapter 6. It has a y-intercept of 1 and a slope of -2. So I go down 2 over 1, down 2 over 1. And you get the idea. Then I'm going to do the same thing for the second linear equation, or I can go ahead and draw my line for my first one. What I'm going to do is then plot my y-intercept for my second linear equation. And I can go again down 2 over 1, down 2 over 1. Now, what's unique about this, and really what part 2 is going to be all about, is we've learned how to solve systems of linear equations by graphing. What we do is we graph both linear equations. We see where they intersect. That's our solution. We check our work, make sure our solution is in fact the solution, that it makes both equations true when we plug in our solution, and we call it a day. Broadly speaking, where the two linear equations intersect is the solution to the system. But in this unique case, we have no intersection. You may have heard this word before, but these lines are parallel. They are parallel lines. These lines are not going to intersect. They're not going to come into contact with one another. That is broadly because they have the same slope. For both ones, I'm going to go down 2 over 1, down 2 over 1, down 2 over 1. So if they do not start at the same point, they will never come into contact with one another, the same point being the same y-intercept. Okay? So since they will not come into contact with one another, what is the solution? Well, there is no solution to the system. What does that mean? That means there is no point of intersection. There is no xy coordinate pair that if I plug it into each equation in the system will make both equations true. No coordinate pair exists that if I plug it into the blue equation and the red equation, it will make them both true. Okay, and that can be seen graphically by there being no intersection between the two lines. So these parallel lines, in this case, special case, there is no solution to the system. Let's work through this one now together. Well, when I look at this one, again, I want to graph the following equations. My goal is to solve this system of equations. The bottom one, I know how to graph very simply, right? Y equals -1/2 x plus 2. My y-intercept is 2. My slope, I'm going to go down 1 over 2, down 1 over 2, down 1 over 2. I'm also going to go up 1 over 2, up 1 over 2. I have my line. But the top one looks a little bit different. We kind of have to dig in the memory bank a bit. I can't just go ahead and plot a y-intercept and slope and graph it because the top equation's not in slope-intercept form. What form is it in? Well, if we think back to chapter 6, our equation is in standard form. So how do I graph an equation in standard form? Well, I have a couple different methods. I could turn it into slope-intercept by getting y by itself. Or what I could do is I could recognize that it is in standard form, and I can graph it using the x and y intercepts. Either method is okay. I'm going to show you how to graph it in standard form using the x and y intercepts because that's the traditional method we learned in chapter 6 when we have an equation in standard form. But if you would prefer to turn it into slope-intercept and then graph it, you may do that as well and you'll get the same result. Again, to do that, get y by itself. So to graph in standard form, we've used the x and the y intercepts for quick graphing. How do I find the x-intercept? Well, the x-intercept, if we remember, occurs when y equals 0. Again, if this is all foreign to you, go back and watch the 6.2, 6.3, and 6.4 instructional videos. The x-intercept occurs when y equals 0. So to find the x-intercept, I'm going to plug in 0 for y. And I get 8 equals 2x because 4 times 0 is just 0. Isolate x, and I find that my x-intercept will be 4. Again, the x-intercept occurs when y equals 0. So I plug in 0 for y, and I find that my x-intercept for my first equation happens at 4, 0. 4, 0. Okay, to find the y-intercept, I'm going to do the exact opposite. I'm going to set x equal to 0. This is because the y-intercept is where you cross the y-axis. Whenever you cross the y-axis, your x value will be 0. So I plug in 0 for x. And I go ahead and solve for y. Again, 2 times 0 is 0. Divide by 4 to get y by itself. And I find that when my y-intercept will occur at 0, 2. The x-coordinate of any y-intercept is 0. I'm specifically hitting the y-axis at 2. So I put it out there. So I found my x and y intercepts. I plotted them. You need a minimum of 2 points to create a line. So what we do is now we connect those 2 points. And I'm sure you are seeing what I am visually, that we have the exact same line. They look very different because they're in different forms, but the line is exactly the same. And actually, if you went the other route, you didn't graph in standard form using intercepts, but you turned this equation in standard form into slope-intercept form, you would have found that you had the exact same line. If I get y by itself, I start out by subtracting 2x from both sides. And then I divide both sides by 4, making sure I divide the whole right side and the whole left side to keep that equation balanced. And that leaves me with 2 minus 2 over 4x equals y. Well, 2 over 4 can be simplified to be 1/2. And lo and behold, when I turn that equation from standard form to slope-intercept, I have the exact same equation. So what happens when you have a system of equations, but you have the exact same line? Well, your solution in this case will be infinite. You have an infinite amount of solutions. Let's talk about why that is. Why do we have an infinite amount of solutions? Well, again, the solution to a system of equations graphically is where the lines intersect. When one line is literally laying on top of the other, they are intersecting an infinite amount of times. They're always intersecting, no matter the x and y coordinate. They're intersecting because they are on top of each other. So there is an infinite amount of solutions. There is an infinite amount of solutions. What that means is whatever coordinate pair satisfies one equation, it will automatically satisfy the other as well. Okay? So we've looked at, in 7.1 part 1, we introduced graphing or solving systems of linear equations by graphing. And now what we're seeing some special cases. Most of the time when you graph a system of linear equations, there's going to be one solution, one point of intersection, one coordinate pair that satisfies both linear equations. But there are some unique instances where there may be no solution if the lines are parallel, or infinite solutions if you have the same line laying on top of each other. So let's look at another example. Graph y equals negative 2x plus 1 and y equals 1/2 x minus 3. Now these are both back into slope-intercept. So I can just jump straight into graphing them, plot my y-intercept, and then do my slope. So I'm going to go down 2 over 1, down 2 over 1, down 2 over 1. Could also go up 2, left 1. And I graph my other line. Up 1 over 2, up 1 over 2. And I connect them with a line. Okay? Now, what do I notice in this case? Well, we're back to only having one solution, but again, this system of linear equations is causing us some issues. Why is it causing us some issues? Because while you can very clearly identify, whether it's on my screen or your paper that you're taking notes on, that there's only one solution because there's only one point of intersection, I'm betting you can't tell me with a ton of accuracy what that point is. We could ballpark. Maybe it's at 1.8, negative 2.1. It kind of looks like. I bet you if I regraphed it by hand a different time, I get a slightly different value. Point is, we did not have that nice, neat, clean intersection where the dots fall on top of each other in this case. So there is one solution. We just don't know exactly what it is. What our solution is going to be is a decimal. Okay? Now, typically when we work with these, when we want to solve systems of equations by graphing, we end up with nice, clean, neat, even solutions. But that doesn't happen here, which means our solution is a decimal. Okay? Our solution is not an integer. And actually what this informs us is that graphing is probably not the best way to solve this system of equations. Well, graphing can be very quick and can be very simple, and it's a great visual. If your solution does not result in an integer, if there isn't a nice, clean, neat, even number, you're going to lose accuracy if you try and solve a system of equations by graphing, and it doesn't turn into a nice, neat, even number. So in this case, what I would do is I would pause and I would go, wait a minute, this is going to turn into a decimal. My solution will be a decimal. I could approximate it with my graph, but I'm not going to get the exact value. I better solve the system of equations with a different method to get the exact value. And again, we're going to learn how to do that in 3.2 or 7.2 and 7.3. Okay, this is where graphing can fall short. When your solution is an integer, it's really nice, neat, quick way to solve a system. That also provides a great visual. But where it can struggle some is if your solution doesn't turn out to be an integer, if those dots are not landing on top of each other, we can approximate our solution, but especially when we're graphing by hand, we're not going to be able to find an exact solution to the system. Okay? And in that case, we're going to use some different methods, or maybe we graph with a graphing calculator or computer to ensure accuracy. So we're not quite sure, right? We could ballpark it, right? I'll use our estimate system. Our estimate here is that the solution's roughly it's about here. So what is that? Maybe we call that 1.7, negative 2.1, roughly, maybe. Again, We're just kind of ballparking here. Now, the other interesting thing to note with this problem, though, not only do I want to show you, we said negative 1.7 or negative 2.1, positive 1.7. The other interesting thing I would point out here is that while it displays how graphing isn't the end-all be-all great way to solve all systems of linear equations and get an exact solution, we can also notice something unique in this picture. Unlike the other ones, this one almost looks like it creates a perfect X. And if we think about that in more mathematical terms, it looks like these lines are creating right angles when they're intersecting, right? They're not intersecting like this, maybe. We're clearly one where certain angles are bigger than others, but these look to be almost matching as if they're all right angles. And indeed, even though I am graphing by hand, I can guarantee you they are. Why? Well, because these lines are actually perpendicular. They are intersecting such that their angles create a 90-degree angle. Okay? Now, how can I tell this even though I'm graphing by hand and maybe my angles aren't totally on? Well, again, just like I could tell parallel lines by looking at their slopes, I can tell you that these lines are perpendicular by looking at their slopes. The slopes of these lines, sorry, I just mixed the colors. The slopes of these lines are what are known as opposite reciprocals. Opposite reciprocals. Opposite, you know what that word means. They don't have the same sign, right? My blue one is negative, my green one is positive. Reciprocal is the fancy math word for saying their fractions or the slope is a flipped fraction, if you want to use common words, a flipped fraction. If we look at the numerical value of these slopes, the blue one is negative 2 over 1. The green one is 1 over 2. Not only do they have opposite signs, but they are reciprocals. The one has the 2 on the top and the 1 on the bottom. The other one has the 1 on top and the 2 on the bottom. When you have opposite reciprocals, different signs in those flipped fractions, in your system of linear equations, it will create those perpendicular lines. So while the slopes are the same, creates parallel lines, slopes that are opposite reciprocals create those perpendicular lines. And in general, we can summarize the special cases in the following bullets. If the slopes are opposite signs and opposite fractions, aka they're reciprocals, one's 2 over 1, the other's 1 over 2, one's 3 over 4, the other's 4 over 3, this will create perpendicular lines. But if the slopes are the same and the y-intercepts are different, the lines will be parallel. Our third special case, if the slopes are the same and the y-intercepts are the same, the lines are going to be identical, right? If it's in slope-intercept form and we have the same slope, the same y-intercept, the lines will be on top of one another. Now, my caution would be, in this last case, you're typically not going to have a system of equations. We're just given the exact same 2 lines. That would be pretty obvious. But typically, we'll see what we saw in the example, where maybe they are the exact same line, but they look different because they're in different forms. But if you turn them into all slope-intercept, or doesn't matter slope-intercept, if you turn them into the same form, you're ultimately going to run into not only the same slope, but they're running through the same points, same y-intercept, and therefore they are identical lines, which produces infinite solutions. Again, remember, parallel lines produce no solution, right? Those graphs don't intersect at all. And then if the lines are perpendicular, the lines will create right angles at their intersection, and but again, they, like most systems of equations, only have one solution. Okay, so again, hopefully this makes sense. If you work through the practice and you struggle, let me know. I know we've covered a lot here in systems of equations and solving them by graphing. So if you have any questions, let me know.